Now let's look at the example that really illustrate how the kind of sliding window that are more useful, more powerful in problem solving. So in the previous example problem, we look at the fixed size sliding window. Here, the size of the window will be changing according to the needs of the problem. So the example problem I chose is a problem from USACO called the cow lineup. And this is the problem description. We are given n cows, each cow standing at a location on a line, and also each cow has a breed number. So we have a single line, and at the different positions there are cows, and the location that appear can be up to 1 billion, and also the breed of the cows can be up to 1 billion. So Farmer John want to take a photograph of these cows. He wants to make sure that there's at least one cow for each breed in the photograph he's taking, and he wants to minimize the width of the graph. So here is the sample input. So we have 1, 2, 3, 4, 5, 6 cows, and there are 3 breeds, 1, 3, and 7. And these are their locations. View them as x coordinates. So we want a picture that includes all 3 breeds, and it turns out that the minimum such window is the one marked by blue. So it has 3 cows of the 3 breed 1, 3, 7, and the size of this is let's call that 4. Just the end subtract the beginning. So we want to find this minimum window in this problem. So of course if we do it brute force, then we'll be considering all windows. So we'll be considering all window and see whether it satisfies the condition, meaning that it contains a cow of each breed. And then we, if it satisfies the condition, then we keep track of its size, and then we find the minimum size. That will be probably, so this will be n cube, because there are n square, order n square, big O n squared pairs, and then to determine what happens in each pair, it will be another linear factor. But this problem can be solved in linear time by first by keeping track the information in the each window more efficiently, so that when we are changing the window, we don't have to rescan through everything to determine the information in the window. And second, by pruning the search space, so we don't have to consider every pair. So the intuition is similar to the how we can prune using 2 pointers. For example, if this window is if this window is good, this from 22 to 26, it has already this 3. We don't need to consider any window that's bigger than this. So we don't need to consider the extending the right side of the window because it's already big. On the other hand, if we have a window that doesn't include all the cows, we don't need to consider any sub window because we know they will not satisfy the condition. So we'll be maintaining 2 pointers, one pointing at the beginning and one pointing at the end of the window. So and in order to, before we process this using this sliding window technique, we first need to sort this all the cows based on their x coordinates. So each cow has 2 pieces of information. So if we store them using a size 2 int array, we want to sort them based on the first element. So this is the comparator for sorting a int array, and I find this code is very useful. So this is actually, this comparator code is in the CP template that I oftentimes I just keep them there, keep it there, and then whenever I need it, I'll just use the comparator. Once you have the comparator sorting 2D arrays, simply calling arrays.sort and pass in this comparator. So after we're reading the data, we first sort all the cows, and then this is how the sliding window, illustrating how the sliding window works. So let's say we start by considering the window of the first element. So it doesn't have all the cows. So then we need to extend the window to the right. So it still doesn't have all the breeds. So then we need to extend the window again. And it still doesn't have all the breeds. It only have breeds 1 and 3. So we need to extend the window again. So at this point, so I use a blue to indicate that the window is good. So the window contains all the cows of all breed. And for this particular problem, our sliding window have the property that when the first time the window becomes good, it will stay good forever. So basically, we will not shrink the window so that it's no longer good, because we only care about good windows, the windows that include cows of all breed. So once we have a good window, we keep track of its size, and then we try to shrink it by moving the left pointer. So in this case, we find out that moving the left pointer works. So the window is still good because we have 2 cows of breed 1. So then we get this window, which is size 5. So this is the best window we find so far. So best means the minimum size. And at this point, we cannot shift the left pointer, because if the window shrink by moving the left pointer, we no longer have cows of our breed. So at that point, we will extend the right pointer. So now we have a good window, but the size will be bigger. And then we try to shrink from left again, and this time we can. So because we have another cow of breed 1. So by doing this, then we get this window, which has a size 4, and it turns out that this is the best window we can find. And after that, we'll extend the window to the right, and then we reach the end. It's still good. We will try to shrink the window from the left, but we find out that we cannot, because if we do that, we'll be missing cows of breed 3. So that's how the sliding window going to slide through this this array. So the step for sliding the window will be big O-M, because we are never going back. So the right pointer always moving to the right, the left pointer always moving to the right, and every step we will be moving at least one of these pointers. Otherwise, we'll be done. We'll just stop the iterations. So to make this linear time algorithm, what we need to do is to make sure for each window, determining its status, determining whether it's good enough, whether it has cows of our breed, can be done in constant time. So what do we need to maintain in order to make that happen? So one thing we need to maintain is what are the number of distinct breed in the window. So we can calculate how many total number of distinct breed in there. In this problem, it's 3. So then we keep track of how many distinct breed we currently have. And whenever that thing reaches 3, then we know we have a good window. Now the question is, how do we update that state efficiently? How do we quickly figure out how many distinct breeds are there in a window? So in order to do that, then we need to remember for each breed how many cows are there. So then whenever we have one breed, the number of cows goes from 0 to 1. Now we know we have a new breed included. We can increment that. Whenever we have a breed that goes from 1 to 0, the number of cows in that breed goes from 1 to 0, we know we have one fewer breed included. And fortunately, updating the number of cows of each breed can be done efficiently, because each time we're just adding a new cow or removing a new cow, And we can use a hash map that map each cow breed ID to the number of cows of that breed, and then we can update it in constant time. So a hash map is needed here because the number of cow breed can go up to 10 to the 9. So it's sparse. So we wouldn't have 10 to the 9 different breeds, but the ID assigned can go up very large. So we use a hash map. If on the other hand, the cow's breed ID are continuous, then there'll be at most something like 10 to the 5 different breeds. Then we can actually use an array. So I think in the earlier topic we mentioned array and a map are essentially conceptually very similar. They are always mapping something to another. Array map index to a value. A map can allow the index, the key to be sparse. So yeah, so I think these slides are the things that I talked about earlier. Yeah, so we want to figure out whether the window contains all distinct breeds. So we need the number of distinct breeds, and then we need the mapping from each breed ID to the number of cows. So that's what we need. So how do we implement this? Where can we use this sliding window technique? So I find that it's often applicable when there's a monotonicity property. And depending on the problem, there are two different kinds of monotonicity. One kind is we want the window to have to include something. So the window has to include things that are sufficient. It has to include sufficient amount of information. So for the problem we just saw, this case, we want the window to include cows of all different breeds. So it has the property that if one window is good, then any window that's bigger, that's containing it, is also good. But there's also another kind of monotonicity property is we want the window to not include too many. So we want to include maybe not include all the breeds. So in that case, if the window is good, the any sub window is also good. So for that we can also use a sliding window because the monotonicity essentially allow us to prune away windows that we know we don't need to consider. So, and the problem that we use sliding window can be counting number of valid windows or finding an optimal window. So according to some matrix of optimality. So in the line up problem, the optimality condition is the size of the window. So the difference of the coordinate from the beginning and between the beginning and end. And to implement sliding window, I find that there are three different approaches. So I tried all three when I was developing this topic, this lecture. So the first approach is in the outer loop. We use a nested loop. We use so an outer loop and inner loop. So the outer loop will loop through all the value for the starting pointer, and then the inner loop will keep increasing the end pointer as needed. So that's one way. And another way is the outer loop is for every possible value of the end pointer, and then the inner loop will keep moving the starting pointer, the left pointer, as needed. And yet another way is we use a single loop. So in every iteration, we will decide whether we move the end pointer or the starting pointer, or we will be returning. So this third approach does not use a nested loop. Conceptually, they are all fairly equivalent. They are all equivalent, and they don't really look significantly different from the other. But just from my own experience of coding it, I find out that actually one way it's just easier to code. It's less prone to bugs than the other approaches. I think at some point I had a little bit more intuition on why that is, but I don't think it's necessarily very useful. And if you don't believe me, you can code all three. So. And if you are really good at, and I think you can code all versions bug-free, there's no fundamental reason that one of the versions is better than the others. However, just from my own experience and also what I observe, I find out one of them is less error prone than the others. And yeah, we talk about the time complexity. So if one step takes constant time, then the complexity is linear time, just like 2 pointers. So because every iteration will be moving the one end of the window by one. And yeah, and the version that I find that's easiest to code is number 2. So our outer loop loops through the end pointer. For some reason, it makes the code easier to write. And this is the pseudocode for using the approach 2 when a problem wants a minimum window. So the outer loop is going through the end, and the inner loop we will be adding each time, because we are considering a new end, we'll be adding the new element into the window. And then when the window is good, we will try to shrink it by increasing start, so long as the window is still good. And for every window, then we can check whether this is a better solution. So we will stop in here when increasing start will make the window bad. Then we will go out and then increment the end. And if we want a maximum window, it's similar, except that after we add this, and if we want the maximum window, then that means the monotonicity probably is an empty window always good. But when the window gets too big, then things goes bad. So we want the maximum window that's still good. So after we end this, we add a new element, it may make the window bad. So in that case, we'll just increase the start until it's no longer bad. We don't need to increment the left further, because well, that gives us good window. That will not give us window of a bigger window, because we want a maximum window, so we don't need to consider those. So, and this is pseudocode if you want to do approach 3, and I only included the pseudocode for the case where we want a minimum window. So we have a starting pointer and end pointer. You need to decide whether your window include from start to end, whether it's inclusive or it's one end that's exclusive. So here I decided to have both end inclusive. So in which case the end pointer is a -1. So this denotes the empty window. If the end pointer is 0, that will actually include the element 0. So then in the loop, I need to consider 2 cases. If the window is good, then first I check whether this gives a better solution. Then because we want a minimum window, then I will, if the window is good, then I will increment the start pointer, and then I need to update the window. If the window is not good, then we need to increase make the window bigger to make it good, in the hope to make it good by moving the right pointer. And if we are outside the range, then we're done. So if the end points to outside the array, then we're done. Otherwise, we'll update the window to include this guy. So yeah, so this is the code for the call lineup problem using approach 2. So I have, so this is, this 2D array stores the call information. So each call have a location and breed in here. And this map will be used to keep track of the number of calls in each breed in the window. And yeah, and yeah, so this is so initially this hash map is initialized so that all breeds are there, but they are all mapped to 0. So then the size of this map will be the number of different breeds. So essentially, while I parse the data, I put in all the keys, all the breeds as the keys, but they're all mapped to 0 at this point. So I'm kind of using this data structure for 2 different purposes. to keep track of the different breeds, and also in the future I use this to keep track of number of cows in each breed. And yeah, so then then this is the second. I loop over all possible ending positions, and because I will be adding a new cow, this is the code for adding a new cow. So I'm incrementing the number of cows for that breed in the window. And if after I increment it, the result is 1, then that means before I add this cow, I don't have any cow of that breed. So then this means a new breed. So it's only when I'm adding a new breed, things become interesting, because then the window will potentially go from bad to good. If I added a new breed, then before I adding, definitely the window is not good. So when this happens, I now have a new breed covered. So I increment breed. If it equals B, then that means now I have a good window. So in this case, I will be keep moving to trying to move the left pointer. So I do that by look at the leftmost cow, and see how many of that breed do I have in the window. If the number is greater than 1, then I can move. So then I will be, when that happens, then I will move the left pointer, increment the start, and then I will subtract 1 from the number of cows corresponding to that breed. And I know this is so this while loop will exit until I get to the window that I cannot shrink further. If I move the start pointer again to make it smaller, I will be losing a breed. So at that point, I will stop. So then I will compute whether this gives me a better or a smaller window. So that's pretty much it for the cow lineup code. So to recap, there are 3 approaches to implement a sliding window. And from my experience, we should always use approach 2. But of course, again, this is it's not absolute. So you can, if you really prefer one of the other approaches, that is perfectly fine.